Alright, let's begin. This presentation covers the landmark AlexNet paper, ImageNet Classification with Deep Convolutional Neural Networks, published at NIPS 2012 by Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton from the University of Toronto. This paper is widely credited with starting the modern deep learning revolution in computer vision. Let's dive in. First, let's look at the overview and key results section. So what is AlexNet? It's a deep convolutional neural network trained on 1.2 million high-resolution images across 1,000 classes. The network has 60 million parameters and 650,000 neurons. It consists of 5 convolutional layers plus 3 fully connected layers with a 1,000-way softmax output. The key result, it won ILSVRC 2012 with a top 5 error rate of just 15.3%, compared to 26.2% by the second-place entry. That's a massive gap. It was trained on 2 GTX 580 GPUs for 5 to 6 days. AlexNet is a deep CNN with 60 million parameters, trained on 1.2 million images across 1,000 classes. It won ILSVRC 2012 with 15.3% top 5 error, crushing the second place at 26.2%. It was trained on 2 GTX 580 GPUs for about 5 to 6 days. The dataset. ImageNet has over 15 million labeled images across 22,000 categories, labeled by Amazon Mechanical Turk. The ILSVRC competition subset has about 1.2 million training images, 50K validation, and 150K test, across 1,000 classes. Images were resized to 256 by 256 and only mean subtracted. No fancy pre-processing. Now we get to the architecture section. These are the key innovations that made AlexNet work. Here's the architecture diagram from the original paper. The network has 8 learned layers, 5 convolutional and 3 fully connected. It's split across 2 GPUs, top and bottom. The GPUs only communicate at certain layers. For example, convolutional layer 3 takes input from both GPUs, but layers 2, 4, and 5 stay within the same GPU. The neuron counts shrink from 253K down through the layers to the final 1,000 class output. This is arguably the most important innovation. Instead of traditional tan or sigmoid activations, which are saturating and slow to train, AlexNet uses ReLU, f of x equals max of 0 and x. The chart from the paper shows that ReLU reaches 25% training error 6 times faster than tan on CIFAR 10. This speedup was critical for making large-scale deep learning feasible. 3 more architectural tricks. First, multi-GPU training. A single GTX 580 only had 3 gigs of RAM, so they split the network across 2 GPUs, reducing error by 1.7%. Second, local response normalization, inspired by lateral inhibition in real neurons, reduced error by another 1.4%. Third, overlapping pooling with stride 2 and pool size 3, which gave another 0.4% improvement and helped reduce overfitting. Here's the full layer-by-layer breakdown in a table. Layer 1 uses 96 kernels of 11 by 11 with stride 4 on the 224 by 224 input. Layer 2 has 256 kernels of 5 by 5. Layers 3, 4, and 5 use 3 by 3 kernels. Then 2 fully connected layers with 4,096 neurons each and dropout, followed by the 1,000 class softmax output. Now, reducing overfitting. With 60 million parameters, this was a major challenge even with 1.2 million training examples. 2 key techniques. On the left, data augmentation. First, random 224 by 224 crops plus horizontal flips, expanding the training set by 2048 times. At test time, they average predictions over 10 patches. Second, fancy PCA color augmentation, which captures illumination invariance and reduces top 1 error by over 1%. On the right, dropout. During training, each hidden neuron is set to 0 with probability 0.5. Forcing the network to learn robust features that don't rely on specific neuron co-adaptations, applied to the 2 fully connected layers. Without dropout, the network overfits substantially. 2 key techniques here. Data augmentation, random crops plus flips expand the training set by 2048 times, and fancy PCA adds illumination invariance. Dropout, setting hidden neurons to 0 with 50% probability during training forces robust feature learning. Both were essential to prevent overfitting. Training details. SGD with momentum 0.9, weight decay 0.0005, and batch size 128. Interestingly, weight decay wasn't just regularization, it actually reduced training error too. Learning rate started at 0.01 and was divided by 10 3 times when validation plateaued. About 90 epochs, 5 to 6 days on 2 GTX 580 GPUs. Now the results. Let's see the numbers. ILSVRC 2010 results. Sparse coding got 28.2% top 5 error. SIFT plus Fisher vectors got 25.7%. AlexNet crushed both at 17%, nearly having the previous best, and ILSVRC 2012, the competition that changed everything. The second place entry using traditional SIFT features got 26.2%. A single AlexNet CNN got 18.2%. Ensembling 5 CNNs brought it down to 16.4%. And the final 7 CNN ensemble with ImageNet pre-training achieved 15.3%. A gap of almost 11 percentage points over traditional methods. Now let's look at what the network actually learned. These are the 96 kernels learned by the first convolutional layer, captured directly from the paper. Notice the GPU specialization. GPU 1 on top learned mostly grayscale frequency and orientation filters, while GPU 2 on the bottom learned color-specific filters. This specialization emerged consistently across every training run, regardless of random initialization. A fascinating result. This figure shows two things. On the left, top 5 predictions for test images. Most predictions are very reasonable. For example, a leopard is also predicted as jaguar and cheetah. On the right, the nearest training images by feature vector distance in the last hidden layer. Even though these images look completely different at the pixel level, the network recognizes them as semantically similar. This shows the network learned true high-level representations, not just edge patterns. And here are the key takeaways. Depth matters. Removing any single conv layer hurts performance by about 2%. Scale matters. Bigger networks and longer training kept improving results. No unsupervised pre-training was needed, which went against the common approach at the time. GPU computing was the essential enabler. And historically, this paper popularized ReLU, dropout, data augmentation, and GPU training, all of which are now standard. It marked a paradigm shift from handcrafted features to learned representations, and directly inspired VGGNet, GoogleNet, ResNet, and the entire modern deep learning era. Key takeaways: depth matters, scale matters, no unsupervised pre-training needed, and GPU computing was essential. This paper popularized ReLU, dropout, and data augmentation. It shifted the field from handcrafted features to learned representations, inspiring VGGNet, GoogleNet, ResNet, and the entire modern deep learning era. That's the paper. Now let me show you how we built this presentation together. It was a collaborative workflow using multiple MUP tools. Here's the workflow. Step 1. The user uploaded the AlexNet PDF into the PDF Reader MUP on the right. I then used the getPageText function to read all 9 pages of the paper and created detailed Markdown notes. Step 2. Capturing figures. I used the setSelection function to draw a box around each figure in the PDF. But since I can't see the exact pixel positions perfectly, I asked the user to help verify and adjust the selection box. For example, here on page 5, I tried to frame the architecture diagram. The user adjusted it, and then I captured it as a PNG image. We did this for all 4 figures in the paper: the ReLU chart, the architecture diagram, the learned kernels, and the prediction examples. You can see the selection box on the PDF right now. This is exactly how the human-AI collaboration worked. I set an initial selection, the user fine-tuned the framing, and then I captured the image. Step 3. I built the slides using the slides MUP on the left. I created 19 slides with different layouts: title slides, content slides, 2-column comparisons, data charts, tables, and image text slides with the captured figures. The image text layout let me show a figure alongside bullet points explaining it. Step 4. We just used the new reading mode to present everything in panel. This reading mode displays slides full screen within the MUP panel with black letterboxing, and I can control navigation through function calls, going slide by slide while narrating with the voice MUP. So to summarize the workflow: PDF Reader for reading and extracting figures, Markdown MUP for detailed notes, Slides MUP for building the presentation with charts and tables, Voice MUP for narration, and the new reading mode for in-panel presenting. All of these MUP tools working together, with human-AI collaboration at each step. That's the presentation. Thank you.